Hi, my name is Leland Green, and this is my lab report for lab number 3, the Black Hole Lab, for Physics 2211. As an introduction, the purpose of this lab was to find the mass of a black hole utilizing the universal law of gravitation, and then find the initial velocity required of a spaceship to avoid entering the black hole. And as a preview, the mass of the black hole was 9.13 times 10 to the 33 kilograms, and the initial velocity was -3 times 10 to the 7 in the x direction and 3.5 times 10 to the 6 in the y direction. Fundamental principles. We utilize Newton's second law, or the momentum principle, where force is equal to mass times acceleration, or momentum, the change in momentum over the change in time, or dp dt. And then we also utilize the universal law of gravitation, where the gravitational force is equal to the negative gravitational constant times the mass of one object times the mass of a second object over the distance between those squared. So for part 1, the mass of the black hole. The system was the black hole and the surroundings was the star. Here's the code. I'll kind of go through that. I used momentum is equal to mass times velocity in the beginning, and then change that to final minus initial to get the change in momentum. Going down, the net force is just equal to the change in momentum divided by the change in time, and then I continue down, and then to calculate the mass I rearranged the universal law of gravitation formula, and then I also added a counter that would add all the masses up and then take the average for me. The mass of the star was provided, and then we also set delta t to the number of seconds in one day. And here was the result. The program outputs all the different masses and then returns the average. For part 2, the system was the spaceship and the surroundings were the planet and the black hole. Here, the code, I utilized the universal law of gravitation, and then we also utilized the position update formula and the velocity update formula to update the planet and the spaceship's velocity and position. And then the distance vectors up at the top were also calculated. The average mass was inputted from part 1, and then the estimated initial velocity was -3 times 10 to the 7 and 3.5 times 10 to the 6. And then the output of this was this video. And as you can see, we avoid entering the black hole. Possible sources of error: limited time running the first simulation. Running it for a longer period of time and with a smaller time step would lead to a more accurate average mass. And the guessing initial velocity in part 2 also could lead to some error since we didn't use an actual calculation or formula. What does it mean? So how is the net force and its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components? Well, the net force is just equal to the net force in the perpendicular direction plus the net force in the parallel direction. Mathematically, here they're the same, and the direction is easy to observe with the arrows in the simulation, but the magnitude is not as easy to measure. On the other hand, the rate of change of momentum is easy to measure and is easy to observe, since all we need is an object's mass, velocity, and a time interval. What if, instead of wanting to take a quick look at the black hole, we wanted to enter orbit? So what would be the required initial velocity? Well, based on the simulation, we were able to do that and the required velocity, initial velocity, was -0.3 times 10 to the 7 in the x direction and 8 times 10 to the 6 in the y direction. In conclusion, mass can be calculated by rearranging the gravity formula, which is Fg equals g big M little m over r squared, And then if you're calculating the unit vector or calculating that as a vector, you add on the unit vector. We also calculated the mass of a black hole. We calculated the initial velocity required for a spaceship to avoid entering a black hole, and also the initial velocity required to enter the orbit of the black hole. We utilized both Newton's second law and the universal gravitational force law, and we also observed the similarities and differences between the changes in net force and momentum. Thank you very much.